All right, welcome everyone to the continuing afternoon session. So it's a great pleasure to have Andreas Stergiou, or Andy Stergiou, if you prefer, from Los Alamos, who's going to give us a talk on conformal bootstrap studies of puzzles in critical phenomena.
Thanks, Miguel, and a big thank you to the organizers for inviting me to talk about my recent work here. So I won't spend any time talking about how we do these calculations, because you've all heard enough of that during the first week. I'll jump straight to applications, the work I've been doing on applications of the bootstrap method to critical phenomena. And many of you probably have gotten the impression that experimentally the situation is quite murky, and theoretically it's quite murky. So I'm doing this with the hope of making it less murky, but with the danger of making it more murky. So let's see how it goes. Of course, I encourage questions along the way. Not that I could avoid it, but you know, I have to say it. So let's start with the case of frustrated antiferromagnets. So let me spend some time discussing this. Perhaps not all of you are sort of like experts on what frustrated magnetism is. So we all know what a ferromagnet is, where the spins align this way, what an antiferromagnet is. There's a case of a frustration where the spins try to align antiferromagnetically, but the underlying geometry of the lattice or the effects of next to nearest neighbor interactions are such that that's not possible. So for example, if you have a triangular plaquette on which you're trying to put the spins, two spins can align antiferromagnetically, but then the third one cannot align antiferromagnetically with both of these. So it's frustrated. It has to choose one of the two options. There are many cases now found in various materials. There is the Ising case, where the spin can align up or down still, where it's just a Z2 symmetry. And the ground state is then degenerate. So there's a degeneracy of the ground state. And however, the spins can also have continuous symmetries. For example, they can have O2 symmetries, they can rotate on the plane, or they can have O3 symmetry, where they can rotate in space. In the case of continuous symmetries, for example, here for O2, we get what are called non-collinear or canted spin configurations. Again, with non-trivial ground state degeneracy, one can check that both these configurations over here minimize the energy. The case of Heli magnets is shown here, where if you imagine a material made out of layers, in every layer, the spins want to align ferromagnetically, but when you move up a layer, there is a certain rotation of the ferromagnetic ordering, and that rotation creates a helix as you go up, a helical structure as you go up the layers, and this gives rise to a Heli magnet. Since this rotation can happen in two ways, again, you have this ground state degeneracy. And this type of frustration was discussed a long time ago in papers by Kawamura during this time, who first started analyzing these physical systems theoretically. And he concluded that frustration leads to physics in magnetic systems that is different from the well-known cases with no frustration. So our interest here will be specifically in the potentially different universality classes that can be encountered in frustrated systems. The idea is that many systems start at a different point. However, under normalization group flow, they all end up at the same fixed point in the infrared. However, there can be, in such systems, distinct universality classes that may be attracted to a different fixed point that we would like to study. So let's discuss why there could be different such universality classes. The Hamiltonian is, again, for the case of frustrated antiferromagnets here, is again just the nearest neighbor interaction Hamiltonian. a little bit more complicated than the usual case due to the fact that these plaquettes here host spins at each vertex. There is at the ground state, however, a constraint where the sum of these vectors adds up to 0. And using this, you can eliminate one of the two vectors for each of the plaquettes in this, for each of these triangular plaquettes in this example. As a result, the effective interactions in the Hamiltonian you will write to describe them will be not a function of just one vector, like in the case of ON models, but it will be a function of two vectors. So starting from the three vectors, the constraint is such that you get these two vectors over here. And the symmetry transformations that will be invariances of this Hamiltonian are these two sets of transformations. One of them is a choice of basis, essentially, where you can rotate what you call phi1 and phi2 with a general O2 matrix. And then you can, of course, rotate these vectors independently, and this will give you another O2, or it could give you an O3 in the case where the spins can rotate in space. So the symmetry group that we encounter in these systems is O2 times O2 or O2 times O3. And since the symmetry group is different than, say, one factor of the orthogonal group, we expect that there might be distinct universality classes. However, there may still be symmetry enhancements under which the fixed points that exist in the infrared or at the critical point are fixed points with more symmetry than this. So there may be symmetry enhancements, but in principle, there could be fixed points with just these symmetries, and their properties could be, critical exponents, for example, could be very different. So assuming just these symmetries and the general case of where we, instead of looking here at numbers 2 and 2 and 2 and 3, we'll put numbers m and n. We can write down this general form of the Lagrangian, which has just the regular kinetic term. I have neglected to write down the mass term. We tune that to go to 0 anyway. And then there are two couplings, U and V. Commonly in the literature, they're denoted by U and V. This over here respects OM times ON symmetry. And strictly speaking, you have to mod out by a Z2 because phi going to minus phi is included in both OM and ON. So you have to sort of mod out by that, by one of those transformations. Here, this phi A are M vectors labeled by A of size N each. And as I already discussed, physical cases realized in experiments have M equal N equal 2 or M equal 2 and N equal 3. But first, I will show you some results for a general treatment of these theories. So let's go to the epsilon expansion of this. You can write down beta functions for these couplings U and V and go through the regular 4 minus epsilon expansion with minor changes from the standard cases like the ON model or the Ising model. But the phenomenology of these are fixed points is quite non-trivial and quite rich. So in the epsilon expansion, there are 4 types of situations you can have depending on the values of M and N. So it can be that you have, or you always have the Gaussian and the Heisenberg fixed point, Heisenberg meaning here O M times N, not just O3. So you have these 2 fixed points, but it can be that you have 2 more fixed points, which I call here C plus and C minus. These are called chiral and antichiral, and they occur in the region where this coupling V is bigger than 0. As you change M and N, these fixed points collide and they disappear into the complex plane, and you are left with this picture over here where you only have the Gaussian and the Heisenberg fixed point, and none of these are stable. Here the chiral is stable. Then as you keep changing M and N, here I should say we'll consider M and N to be fractional as well. We'll just consider them as continuous parameters. The fixed points that disappeared may now reappear, but they can reappear in the so-called sinusoidal region where V is less than 0. And then they can still move around, and one can move into one can stay in the sinusoidal region, and the other one can go to the chiral region. and then the Heisenberg one may be the stable one. Depending on M and N, and you can compute the M and N for which these transitions happen, you can compute them in the epsilon expansion as a function of epsilon and find exactly the regions, if you want, for M and N for which you are into any of these 4 situations. But of course, the physics we're interested in the materials we're interested in, are in 3 dimensions. So you have to take the epsilon to 1 limit. And it's not clear what the boundaries of the regions for M and N are, or what exactly the qualitative behavior is for a given integer M and N once you go to 3D. So that's sort of what we want to study with the conformal bootstrap, which we can do directly in 3D in non-perturbative way. So before we start, let me just describe very quickly the ingredients we need for the plots that I will show you in a little bit. So the essential one is that we need to know the representations exchanged in the phi OPE. So the phi here is not a vector, it's a matrix. You can view it as a matrix if you want. And the rows are like the OM and the columns are the ON, transform under OM and ON. So since this is a product group, OM times ON, we know that the irreducible representations will be the product of the irreducible representations of just one orthogonal group. So basically you take the singlet, the traceless symmetric, and the antisymmetric of ON, and you just multiply them, and you're going to get 9 distinct representations. So by SS here, I mean, you keep the singlet from the OM and the singlet from the ON. And here is the singlet and the traceless symmetric, and so on. These over here will be exchanged for even spin, and this will be exchanged for odd spin. There will be 2 conserved vectors here. One conserved vector will be in this SA representation, and there will be 1 conserved vector in this AS representation. And then there will be further operators starting at spin 1 and spin 3 and so on, which don't necessarily contain any conserved spin 1 vectors. So this OPE is essentially enough, all we need to bootstrap the 4-point function of the operator phi, and as well as the 4-point functions of phi and the operator SS, which is the singlet, if you want, of this group, because this has no indices. It's easy to add it to the bootstrap problem with minor complication. You just get a larger minor complication coming from group theory, and you just get a larger bootstrap problem to solve. So in the following, I will do some relabeling. I will call this SS. I will just call it S, the singlet. In the plots, you will see TS will be what I call W, ST will be what I call X, and AA will be what I call Z. So these are all, by what I mean by these are the spin 0 operators in these sectors, which of course have spin 2 and even spin operators. Okay, so let me show you the first results, the first numerical results. These are from a recent paper with Johan Henriksson and Stefanos Kouzvos. They were also, the plots that were also discussed and obtained in an earlier paper by Nakayama and Otsuki. But what we did in this paper, we also used results from the literature and results we derived at the large N, for the large N case. So you see here I have put M to 2, and I'm increasing N. And in this case, you can compute large N results for the fixed points. We start from the O2 case, and there is a very mild kink, as you see here. And this kink sort of gets much stronger as we move to higher N. So for the O220 theory, it's a very strong kink. And the squares here correspond to the chiral fixed points, and the circles to the antichiral fixed points. So what we see, especially up here, where the large N results are trustworthy, is that the kink is saturated by the antichiral fixed point with the chiral fixed point in the allowed region. This is how it works.
I forgot which one was stable, chiral, antichiral.
Antichiral is unstable. So if we go back to this picture, we're in this figure over here. Chiral, this C plus, is the stable one, and antichiral is unstable. And the unstable is the one that saturates this W bound, W being this TS operator. Okay.
Is there any way to remember why one is called chiral, one is called anti-chiral? Because yes.
I don't know of a way to remember that. I mean, I think, you know, in these cases, when you add one coupling to ON, you get two fixed points and people call them one and anti the other. You know, I don't think, the important thing to remember is that they're called chiral because they appear for a V larger than 0, which has implications for the minimization of the energy and for which system they can describe. The fact that they are calling them chiral versus sinusoidal is different, but chiral versus antichiral, I don't think is, I don't have a physical justification for the name.
Okay.
So the antichiral fixed point here saturates the bound in this W sector. So by W here, I mean the leading spin 0 operator in the W sector. Okay, so now let's go to the X sector. In the X sector, the situation is sort of reversed. So first, let me show you here that in the X sector, there are strong kinks.
Sorry, can I ask you just to not? How do you know that this kink corresponds to one of these critical points and not the others? I mean, how?
Oh, I can make this determination at large n because I have trustworthy estimates at n equal 20. So I have a one. I should mention here that these are taken from, I mentioned it later, papers by John Gracie, who computed at large n, particularly for this dimension of W, it's from our work where we computed at large n where delta W is. So delta W will have some dependence on 1 over n, and then 1 over n squared, and 1 over n cubed. We forget about the 1 over n squared and the 1 over n cubed. We only look at the 1 over n term, but at n equal 20, we trust that the result is pretty good. And when you plug it in for the chiral or the antichiral, you get these 2 points here right on the plot. And you see that the kink is saturated by the antichiral solution.
For example, the Heisenberg point, where it is?
So this W is sort of, in the Heisenberg case, is sort of part of the traceless symmetric. So if you go to the O220 theory, you have to look at the O40 model. And the O40 model has a traceless symmetric representation with dimension, which I think is very low, close to 1. So the O40 model would be down here. Down here somewhere.
Okay.
I didn't put it on.
And the Gaussian, by the way,
the Gaussian is just here at the point
okay.
0.51, because this W operator is sort of quadratic in the field phi, which has dimension 0.5.
Yeah.
So the Gaussian would be down here.
Okay, thanks.
Okay, great. So I was showing you that you see here, one fixed point saturates the bound and the other one is in the allowed region here. And the geometry of the bound, at least before it reaches the fixed point, is, you know, quite spectacular. It goes up very strongly and then to the right. Here, I'm showing you the X bound. So this is the operator ST. And again, we have a kink. It's milder, mostly because, you know, you have the linear relation here beyond this point, the linear sort of curve here beyond the point. But here, it's the curvature is different than in the previous plot I showed you. If we plot now, again, use our large N results to put the same fixed points on these bounds, we see that the kink, for example, in the 220 case, this is a little bit washed out, I hope you can see it. The kink is now saturated by the chiral fixed point. And the antichiral fixed point is in the allowed region, but it's kind of on the left of, and perhaps this is why the bound doesn't have the curvature that it had in this case, where there was no fixed point here to sort of like push it out. So this was quite interesting because we do two different plots in two different sectors. And in one sector, we know we have two fixed points, at large n at least. We certainly know we have two fixed points because at large n, we have different methods to compute, and also the epsilon expansion is more trustworthy. And one bound, the W bound, is saturated by one fixed point, and the other bound, the X bound, is saturated by the other. So I think that's quite interesting behavior for this particular case. And then we took and we did the mixed correlator bootstrap involving this operator that I call phi and the singlet operator S. So when we did that, of course, we had to impose various assumptions, but imposing these assumptions, which I'm not going to go into much detail in, we got these two separate islands for here shown for the 210 theory and the 220 theory. So in blue here, you see the location of the fixed points according to large n results. And these large n results, for example, include the 1 over n squared corrections, which were taken by from this paper by Gracie, and you see that the islands happen to occur in very good sort of agreement with the expected with what's expected from the large n results. Unfortunately, I don't have a way to assign errors to these large n results, but this is the picture we get. Regarding assumptions we made for these islands, in case people are wondering, there were minimal assumptions, but there was an important assumption that we were saturating these bounds I showed you earlier. We were assuming that the dimension of this X operator, for example, was on the bound. And we were making an assumption that there was a conserved current, and then there was a small gap above that conserved current. And finally, we were making an assumption that this next to leading singlet was larger than 3, had dimension higher than 3 for the chiral fixed point, and higher than 1.5, I think. Sorry, 2, I think, for the antichiral fixed point, which anyway is supposed to have a second relevant of, it's supposed to be tricritical, the antichiral one. So this is a case where we have 2 fixed points expected, and we got 2 islands, which is quite nice. And with more recent, they're kind of oddly shaped. And I think that with more recent, with the more recently developed tools in the Bootstrap, we can make these a lot better. Okay, so let me now go to another question that has been discussed quite a bit in the literature. Let me go back here. So now you can ask, okay, we are in this regime when we have the 220 theory and the 210 theory where everybody believes we're in this regime. But then when does this change happen? When do we go from at what n? So we'll fix m to 2, and we will ask at what n do we go from this behavior to this behavior? And the wide agreement in the literature is that this n is somewhere around 6. So this is this has been discussed by people that do epsilon expansion, has been discussed by people that do functional RG, and with the Bootstrap, we were able for n equals 6 for the 2,6 theory to obtain an island using assumptions you can find in the paper, and we managed to look at here the chiral fixed point according, this is for the chiral fixed point specifically, according to large n calculations, it's supposed to be here. And according to the most recent, I should say that this large n computations again include the 1 over n squared results. And these computations here in the epsilon expansion are up to 6 loops. So up to order epsilon to the 6 in this case. And they also have resummations and various tricks to improve the convergence of the expansion, and they give errors for the location of the 2,6 chiral fixed point, which I also plotted here on the same graph. So according to the epsilon expansion at 6 loops with resummations, the 2,6 theory is supposed to be here. Our Bootstrap calculation is finding it right here, and obviously we need to improve our this is a quite large island. We need to improve our numerics. We need to use the newest tools to make this much smaller island and examine better the conditions for the existence of this theory, the 2,6 theory. Okay, so this was more of the.
But so do you see any sign that, for example, for 5 this no longer exists, or some disappearance of this line of fixed points collision? Do you see any sign of that?
Unfortunately, here we don't. And let me go here to these plots. One reason may be that, these fixed points are not both on the bounds, right? One, as far as single correlator bounds are concerned, it's different than cases that have been discussed here in this workshop. For example, Shai just discussed his case where kinks were both on the bound. Here is different. It's different. Here we know that one kink saturates, the other is in the allowed region. Both happens in the sector. I don't know. That doesn't allow us to see this at the level of single correlator bounds. At the level of islands, it's even harder. But you certainly would like to see the island for the antichiral case and something happening, but we haven't seen that.
So you should see that 2 islands, perhaps they first separate.
They're supposed to move
start
closer.
Getting close to each other and then move on top of each other.
Right, and you can see it here already. Well, it's not. You would say that these islands are farther away a little bit than these islands. I mean, it's not clear here, but if you do it for lower n, you should see those islands coming to closer and eventually disappearing, but we have not seen that. But this is what you expect to see, of course.
Okay.
Sorry, Andy, I'm a bit confused about this figure. So you are.
About which one? Sorry.
So in this case, with n equals 6, so the prediction is that there is a fixed point, but then it's lying outside your island, or.
So the prediction is that that in this case 2,6. Let me go back. That we are still in this graph, and there are 2 fixed points. The chiral and the antichiral, they still exist. And in this case, we managed to get an island. And there is a separate prediction from the epsilon expansion of where the chiral fixed point should be, which is this rectangle over here. And there is some tension. This is what we got from the bootstrap, the green region. There is some tension with the epsilon expansion. But I think we need to, to make it more precise, we need to do a lot more work to understand exactly.
Is this a feature or a bug?
What do you mean a feature or a bug?
I mean, do you expect the fixed point to exist or not? You see,
yeah,
there is a tension. There is a tension. It seems like an understatement.
So we expect the fixed point to exist at n equals 6, and we expect the fixed point to disappear somewhere between 5 and 6 if you believe the results of the epsilon expansion and similar results from the functional RG community. With the bootstrap, we have not seen the disappearance of the islands. I have not, in this work, we have not seen that. But presumably, we should be able to see it, with more work. But in this work, we have not seen that disappearance of islands.
So what value of n does the epsilon expansion give for the merge of the 2 6 points?
I think it gives something like, for m equal 2, it gives something like n equal 5.89 or something like this. Close to 6. But this is in this paper by Companies and Company from a recent paper, which is the 6-loop epsilon expansion calculation, this OM times ON theories. So this is not a conclusion. This is just to say that the bootstrap allows, at least at the level we used it, allows this green region over here. More work clearly needs to be done to show if there is, how much tension there is with the epsilon expansion, and if there is an island for n equals 6, and if it persists for n equal 5 and n equal 4 and so on.
Do you see, for example, we know on theoretical grounds that when the certain fixed point collides and when they disappear, You expect on theoretical grounds that there should be that this the second operator S prime, let's call it, should become marginal or nearly marginal.
Well,
So
one
do you
problem
see
is,
any
of course,
signs of that?
Yeah, one problem is, of course, that we have such a large island here. It's kind of hard to look for that. And the associated kink is also quite mild. And if you just look at the spectrum, I don't have much trust in the spectrum in that regard, in the spectrum reconstruction. So I don't want to say anything more than that. I just don't know at this point.
How does this tension, as you call it, change with your assumptions on this?
Sorry, I missed it.
You get this island, you made some assumptions. So
yeah, the assumptions are very mild here. They're very mild. We just assumed that the second singlet here, since it's the chiral fixed point we're looking at, should be above marginality, and we just assume that there is a current. One of the two currents is there, and there's a small gap above the current, above one of the two currents. That's all we assumed for this plot.
So there's no way to improve this agreement.
We haven't. The gaps we put are small. So if you start to increase the gaps, you'll start getting a tighter region. But we didn't want to, because we don't know the spectrum from some other way for those operators. For example, for the operator that's spin one, but not the current, the next one, we don't know its dimension. We don't want to put assumptions in that may exclude the theory. So we try to put as mild assumptions as we could, and then we end up, of course, with a large island. The fact that we get an island with with mild assumptions is good, but if you ask for more, then I think this is the usual problem with the bootstrap, right? If you don't know what assumptions to make, you're going to have a problem.
No, I was asking to ask for less, maybe to reduce this tension. This is my question.
Oh, to make it. I don't remember specifically everything we tried, but we tried many things, and things weren't changing that much. I mean, the tension with the result of the Epsilon expansion wasn't getting resolved just by making the assumptions. The already weak assumptions make them even weaker.
But maybe this tension is a red herring, because they do have big error bars, and it's within like 2 sigma with respect to the error bars. So
yeah,
I wouldn't be very worried about the tension.
Yeah, I'm not very worried either. But I just want to present the full picture. So
Andy,
yeah,
you mentioned that the critical n in this case is between 5 and 6.
That's what's believed from Epsilon expansion calculations and from the FRG community. Yes.
Yeah, but in your single collider bootstrap band, you still have kink when n equal to 5 or 4. Can you go back to the slide?
Yeah. You're right.
So that means if we identify this kink as the signal of the IR fixed point, then can we expect that the critical n is kind of smaller than 4, or?
The presence of the kink, I think you're right to think about it this way. It's a very interesting case in which there is a strong kink here for the antichiral fixed point even from the 2,5 and even for the 2,4 theory. Not as strong, but it's clearly there too. Mm-hmm. It's a good case to study further, especially perhaps the new tools that people developed will help us in this example, study further and understand where the fixed point disappears based on the mildness of the kinks further with islands. If you look at the X sector, the kinks are much milder, although there are these qualitative changes in the shape where this is linear and before here it's like curved. So there are still signs of fixed points here, but certainly from the W sector, which is saturated by the antichiral fixed points, the signs are much more clear. And it's not clear to me. Let's just say that it needs to be studied more, and it's a great case to study more because we have features that theories, other epsilon expansion and so on says that there aren't fixed points associated with these features. So it's a great case to study, I think.
Okay, thanks. And also go back to Slav's question, right? So near the critical NC, so which operator do you expect that like either from the epsilon expansion or from margin expansion that will become marginal?
The second singlet, the next to leading scalar singlet.
Okay. So in that case, to test if there's an operator near the marginality at like the n equal to 6 or 5, I guess one way you may try is that here you find the lowest singlet, right?
Mm-hmm.
So you may impose a gap for the second singlet. It is slightly above the marginality condition, the delta equal to 3. You may impose gap like 3.2 or 3.3, and to say if this island will disappear. Yeah. So if indeed there's the second operator approach marginality condition, then after imposing this condition gap assumption, then this island should be killed. Yeah, we didn't play much of this game as part of this paper, but again, this would be a great thing to study. Yeah, I think it's interesting. Also with increased, with stronger numerics than we used to get a much better estimate we didn't really offer an estimate for this value, this critical value of n for which the island disappears, but I think with the bootstrap we can do it, and it's worth doing. Yeah, and also I don't think here is a tension between your island and the epsilon expansion result, because after all, it's epsilon expansion is a perturbative result, and for small n and at 3D we know that the area bar from the epsilon expansion is kind of little. So I don't think the epsilon expansion result is very reliable at n equal to 6. So it's fun. There's a difference between your bootstrap result and the epsilon expansion result. Yeah, I tend to agree with you, but I just want to. I don't want to make any strong statements about one thing not being reliable or not, but. This is the picture I get. If we can improve on it, from the bootstrap, that would be great. Okay, thanks. Thank you. Okay, great. So since we discussed the theory now a little bit, the more theoretical academic questions, now let's go to questions that may be more interesting for experiments. So I just wrote down here again this OM times ON theory. And just to say that for m equal n equal 2, so remember, we're going to go now back to the O2 times O2 case. So that's a case where potentially experiments are sensitive to. And in this case, this Lagrangian over here has a symmetry enhancement. So instead of having symmetry just O2 times O2, it's going to have O2 times O2, but there's going to be a semi-direct product with Z2 or S2. That emerges. This action of the semi-direct product is to basically exchange these O2s, and we will assume, so this happens at the Lagrangian level, but we will assume that it happens also at the non-perturbative level, okay, to examine these systems. And because, in theory land, you can, once you see something like this, you want to generalize it, we're going to consider bounds on this so-called MN theories. MN theories have two, again, indices M and N, and they are semi-direct products of this type, okay? And just to reiterate, the M equal N equal 2 case describes this XY stacked triangular antiferromagnets. It describes niobium dioxide. I think this was mentioned in Pierre Toledano's talk, niobium dioxide, and also describes phase transitions in holmium, dysprosium, and terbium. It's supposed to describe such phase transitions. And for M equal 2 and N equal 3, these MN theories are supposed to describe things I don't know how to read from chemistry, but this is neodymium, okay? So, and we'll see some results for those. So let's look at these MN theories now. So I did some work on these theories back in 2019. Again, you look at the 5-IOP. Here, the group theory is a little different, but okay, you work it out and you start getting bounds. There is a sector X. It's not the same X as before, but this is sector X. And for the 2,2 theory, you see a strong kink. And then you look at the 3,3 theory, 4,4, blah, blah, blah. You see, again, the kinks move in this way towards this point 1/2, 2. And in a more recent paper, again, with Johan and with Johan Henriksson, we were able to compute large N results for this, large M rather, not large N, large M, the first index. And we were able to put crosses and dots on these plots
And the dots correspond to the large M results here for the same theory. The crosses correspond to the epsilon expansion, where we take the results of the epsilon expansion up to order epsilon cube, and we just send epsilon to 1, okay, without resummations, without anything. And this is where the fixed points lie. And you see again that as we look at large N, so this is a 30,2 theory, very good agreement with the position of the kink and this dot, which is the large M result, which includes only, I repeat, the leading order value for delta X. These results for this theory, large M results, were not computed before this work. So again, we have strong kinks. And now let's look at the experiments for particularly the M = N = 2 case. So here people did experiments, and I'm going to give some tables that I took from some review work by Delamotte and collaborators. I'm not going to give references.
Can I ask a question, Andy? So I'm just confused. So you said that there's a symmetry enhancement and so on, but before you said that these fixed points disappear for M less than 5.8. I mean, in the previous story. So now we are considering it.
Yeah, but you know, they can reappear.
Under which in which how you say identity do they reappear? As this S plus thing or what?
Yeah, so you'll see that they appear here according to the epsilon expansion. Okay,
I see.
I'll show you these results.
Okay, thanks.
Mm-hmm. Okay, where were we? Here. So I was starting to talk about the M = N = 2 case, where people believed then that there is this O2 times O2 with the enhancement theory, and working out the Hamiltonians, they said, oh, this theory should describe phase transitions in various materials, this XY STAs, this is stacked triangular antiferromagnets, and they measured critical exponents in various, these are different experiments, okay, for these compounds. And they found these guys over here, and they measured terbium, which is a Heli magnet. So there is a paramagnetic to Heli magnetic phase transition in terbium. They found these numbers. But then they measured holmium and dysprosium, and they found these numbers over here. So I grouped together in colors green, this same sort of like looking numbers, and in blue, these other same looking numbers. So that was a surprise because there's supposed to be one theory describing this. However, the critical exponents are clearly incompatible. And I should also mention again that there is a structural phase transition in niobium dioxide that has critical exponents seemingly in this group. Okay, so what are the results from the RG methods? The results from the RG methods are that the epsilon expansion, this was worked out in up to 4 loop order in this paper from 2001. I think they also did some resummations, and this fixed point in the epsilon expansion occurs in the V less than 0 region, which is the sinusoidal region. This answers Slava's question. And it has these critical exponents.
But is this what you expect? Because you said there's a Heli magnets. I'm just trying to understand.
Yeah,
the
so
connection.
that's what the question mark is here for. The epsilon expansion at leading order gives you a coupling V less than 0. Now, if you want to trust that at epsilon = 1 or not, is a little, you know, it's questionable. But certainly, close to 4 dimensions, the coupling solution of the beta functions gives you V less than 0. So it would appear to be in the sinusoidal region and not the chiral region, which is the region that is supposed to describe the Heli magnets and the STAs. But this is the leading order result of the epsilon expansion. If you keep other orders, if you send epsilon to 1, I don't know how to conclusively say that in D = 3, this V is less than 0. This would be
But what do you mean? But people who resum beta functions and so on, they know. Or you mean that they don't resum the beta functions, they resum critical exponents, and then
in
things
this
may happen.
For this paper.
Okay.
These other papers, people resum beta functions. So there, of course, as you know, there's 2 different. Look, I'm not an expert on these. I'm familiar with the epsilon expansion, of course. I've worked on it, but. And certainly the situation here is as I said, at leading order in the epsilon expansion, you get the coupling V to be less than 0. So you wouldn't expect this fixed point to describe XY or STAs or Heli magnets. You just wouldn't, because it's not in the right region. Those require V larger than 0. But I don't know if it's true, given that we will see that the epsilon expansion appears to anyway underperform here. So let's put that question aside for a little bit, and let's go to this fixed point. So this fixed point, it's the same fixed point, supposed to be the same fixed point, found in papers by Perisetto, Rossi, and Vicari, so and collaborators. So these fixed points occur when you look at the fixed dimension expansion. You write down the beta functions the same way you write them in Numerical. You send epsilon to 1, and then you resum the beta function, and then you look for fixed points. It's kind of I don't know, it's not a controlled thing to do, let's say it that way. But it turns out that there are more solutions then that people call the chiral fixed point, because it occurs for V larger than 0. And these are the solutions proposed by Perisetto, Vicari, and collaborators to describe this XY stacked triangular antiferromagnets. And depending on what way they use to resum the beta functions, the scheme they use to do that, they get 2 different sets of critical exponents, but this is supposed to be the same fixed point. Okay?
So these are fixed points which are not connected to the 4 minus epsilon dimensions.
They are not connected to the 4 minus epsilon fixed point, yes. So I think this was also a question that Amnon Aharoni had at some point, if there are ever proposed fixed points that go beyond, if you want the standard Wilson-Fisher paradigm. And these have been proposed to be such fixed points. Okay. Now, there was also a Monte Carlo study. Again, I'm not giving references, sorry about that, but you can find this in this review paper in STAs that are supposed to apply to STAs, where they found some critical exponents here, which are quite curiously close to terbium and the other stuff. These appear to be quite close to the holmium dysprosium critical exponents. These appear to be close to terbium and the stacked triangular antiferromagnets, but the Monte Carlo simulations invariably in these systems give some weird negative etas, which means that unitary or beta over nu which is the dimension of what we call phi typically, is below ½, and therefore we have a violation of unitarity in that the order parameter operator is below the unitarity bound, which I don't understand. But if there are Monte Carlo experts, I would be very happy to hear more about why such negative etas appear in these Monte Carlo simulations.
But did their latest model satisfy reflection positivity?
I think so. It's just the spin models that we discussed.
Okay, but they have some antiferromagnetic coupling, so maybe there's some subtlety. No, there's no subtlety.
I'm not sure, but I would like to understand this better. I think this is important to understand. And I should say that this happens in this O2 times O2 theories, but it also happens in the O2 times O3 theories that have also been studied with Monte Carlo by Kawamura and other people. And they again find these negative etas in those simulations. Okay, so
I think it's just wrong. I mean, one could even, if they see it in finite volume, one could just look at but this is probably extracted from the finite size scaling, not from the 2-point function. So one cannot really rule it out. Yeah. Okay, sorry.
So here you can try to perhaps resolve this by saying, well, maybe beta is underestimated or nu is overestimated. You could, because the sign is basically the distance of beta over nu from 1/2, right? So if beta over nu is less than 1/2, you get this negative eta. So perhaps beta has been underestimated, and that's what I will suggest in this, or has been, Anyway, the evidence for two of these two different types of phase transitions prompted me to look at this 2,2 theory and look at the larger part of the parameter space. So this is the same plot I showed you before, but I focused on this region over here. But when I looked further, there was a mild second kink. Okay, this is a mild kink. Nevertheless, it's there. It's certainly a qualitative change in the way the bound behaves. And the question is, of course, the theory that describes the systems didn't have to be on the kink. It could be anywhere in the allowed region. But perhaps it would be non-trivial if working out the spectrum at the kink gives critical exponents that are in good agreement with the experiment. So that's what I did next. And here I summarized this.
Andy, I have a question. For that second kink, do you have a plot of, say, the second derivative to see if it has like a sharp spike at that region?
I don't actually.
Yeah,
I don't.
Yeah, because like something that sometimes happens is that you know, and this is something I've observed myself in the case of the Potts model, is that like, you know, like a plot can change, but it can change gradually, and then it can be a little bit tricky to know exactly where the kink is.
That's right. That's right. And I haven't done that. That's a good suggestion. Okay, so let me summarize here the results I have shown you so far. So niobium dioxide is supposed to have this beta. Holmium dysprosium have this beta in nu. This is from some experiment. They didn't measure nu. And terbium and XY stack triangle, I averaged them basically to these numbers over here. Just took those tables from before and averaged things. Again, here there is the unitarity issue, even in the experiments in some region of these. You know, remember beta over nu should be larger than a half. So there is some tension with unitarity even in the experiments, which I want to say is a sign for underestimating beta. But anyway, so here are the results from the RG methods. And here are the results from the spectrum reconstruction, which allowed me to determine beta and nu from the bootstrap. So beta in the first kink for the 2,2 theory is this number over here, and nu is this. So the errors here are estimated based on how the bound moves and the spectrum changes as I increase the strength of the numerics. So don't take them, you know, as gospel, but I hope they are conservative enough to be correct. And in the second kink, beta came out to be this number and nu came out to be this number. So I consider this evidence for two distinct conformal field theories with these sets of critical exponents, which are in pretty good agreement with experiments, I would say. So the second kink perhaps describes this class of experiments, and this first kink perhaps describes this experiments. And I should also say that the epsilon expansion is supposed to correspond to this solution over here, to the first kink. And the reason I say this, let me go back a little bit, is that if I do epsilon expansion, we can very well say that this kink is the kink of the epsilon expansion at these large numbers. And the way it moves, it smoothly moves to this one. So we assume that this is still the kink corresponding to the epsilon expansion solution, even at the small values, although we cannot directly verify that. So this is an assumption, but based on the way the kink moves, I think it's a pretty good assumption. So resummations of the epsilon expansion show that perhaps if this is a bootstrap non-perturbative results in d = 3, they're quite different. So perhaps the epsilon expansion underperforms quite a bit here. People saw this beta, that it was good in good agreement with this holmium dysprosium and niobium dioxide, and then nu, of course, is not. So as I said in the very beginning, the situation is murky, but I think the evidence for two distinct CFTs now from the same method, because before there was sort of evidence for two distinct CFTs perhaps, because the Monte Carlo simulation gave something closer to these guys, and the perturbative, the RG methods, the epsilon expansion and the this fixed dimension expansion gave something closer to this. But now we have one method, the bootstrap, which gives estimates for critical exponents that may describe both these theories. And I think this is good evidence for two distinct CFTs. But at this point, it's evidence and requires more study that I hope we will undertake in the future. So let me show you now another result for the O2 cubed semi-direct product with S3 theory. And here the epsilon expansion was giving a very good agreement for the beta critical exponent with the experiment in neodymium. Neodymiums are these very strong antiferromagnets. You can buy them, and they are very strong, impressively strong. They are antiferromagnets, and then they have a paramagnetic to antiferromagnetic transition. In this transition, the critical exponent beta was determined in experiments, and it was a very good agreement with the epsilon expansion. When I did the bootstrap, again, for this theory, I found two kinks. Now the second kink is actually much stronger for this 2,3 theory. I believe that this first kink is the theory of the epsilon expansion, and this corresponds to these numbers over here. So again, there is quite a bit of tension with the epsilon expansion. And then there is a second kink out here, which has these numbers. And it seems that neodymium perhaps is described by the second kink as opposed to the epsilon expansion kink. So these are the results I wanted to show you for as they pertain to experiments in this ferromagnets. But recently, we did some further studies of these theories with Johan. And we found that these second kinks, if you want, they persist at larger m. So you take the 2,2 theory, there was this mild kink. In the previous slide, I didn't change m, I changed n. I went to the 2,3 theory. But now I go to the 20,2 theory, and there is the very strong kink that is certainly the theory of the epsilon expansion. And then another, milder kink, of course, out here that persists. And we tried for even larger m's, and we see the kink for the theory 30,2, 50, 100, up to 1,000,2 theory. They all have this kink. So this kink, the second kink, appears to be, part of a family of, putative CFTs, if it's saturated by such a CFT. It doesn't. There are sometimes second kinks that are, correspond to some jumps in the in the bounds, which can be perhaps explained from other ways. But this sort of like smoothly moves as we change the parameters here, and there is no jump or anything. So this suggests that it may be a real non-trivial conformal field theory that saturates it. But again, I think this is an interesting thing to study. Okay, so this is what I had to say about this ferromagnets, and I think this is an important question, in particular for the antiferromagnets, the stacked triangular antiferromagnets I showed you, is if there are really truly two different universality classes, one has to ask what determines the fate of the theory in the IR. Which fixed point attracts which theory? Why does terbium and the STAs go to one fixed point and holmium and dysprosium go to another? So I think this is a very important question. You have if we really have two distinct universality classes, this will allow us to examine further conditions that determine, in a sense, the basin of attraction of these two distinct fixed points. So the physics here can potentially be very rich. So let me now show you some results. Sorry, was there a question? No. Let me show you some results about the O2 times O3 theory.
Sorry, maybe I can ask a question. Did you also do some studies where you vary the space-time dimension?
No, but that is definitely an option. Perform studies in these theories in the 4 minus epsilon expansion and examine, for example, one interesting thing would be to examine when do deviations of this that I'm describing here, when do they start to really appear? And can we trust the epsilon expansion results, sort of determine an effective radius of convergence, if you want, of the epsilon expansion in this case?
The other question is, in this second kink, so you also looked at the spectrum to see what's happening around that second kink?
Yeah, that's how I determined the critical exponents. And I should say that both this, the next to leading singlet is supposed to be irrelevant from the spectrum. And so this is supposed to be both stable fixed points. Okay. Now, this there's another class of stacked triangular antiferromagnets that are described not by O2 times O2, but by O2 times O3. And there was a paper by Nakayama and Otsuki, I already mentioned it some time ago, where they obtained a bound on this W operator, and there was a mild kink again, and they speculated that this may be the fixed point that describes the stacked triangular antiferromagnets of the O2 times O3 class. So we improved on this by obtaining an island, again with very mild assumptions in our work. Again, I'll show you some experimental results. So this was the island for the so-called chiral fixed point. There is another fixed point that is supposed to exist in this O2 times O3 theory called the collinear fixed point. And again, Nakayama and Otsuki suggested that this collinear fixed point is found when you saturate this delta Z bound. So this Z is the AA operator. So you take the antisymmetric from both O's, and that gives you a scalar and the singlet, a scalar transforming in this Z representation. And it has the bound and the kink. And again, here with very mild assumptions, we were able to get an island for this. And here are the results for this O2 times O3 case. So these are the bootstrap results from our work and also from the spectrum analysis of Nakayama and Otsuki. And this phi is just some crossover exponent corresponding.
I'm confused. So it's O2 cos O3. Again, what is the relation to your previous thing saying that the theory should disappear, the fixed point should disappear below 5.6? Has it already reappeared?
They're not supposed to be related, because for 2,3 there isn't supposed to be this description from the epsilon expansion. But again, Pelliceto, Vicari, as you'll see here, and collaborators have done these resummations, and even in this case have found fixed points with the right coupling sign to describe these phase transitions. And experiments have seen these as second-order phase transitions.
Okay.
So for these low values of M and N, the epsilon expansion results are not the ones that people believe are trustworthy. Well, but there are these extra fixed points again from the fixed dimension expansion.
Okay.
Okay, so these are the numbers. And the experiments in this STAs, you can find these results in the big review by Pelliceto and Vicari if you're interested. There's various tables in there with explicit references to the experiments. For the chiral and the collinear fixed points, we found these numbers. Sometimes the agreement with theory between the theoretical methods is good, sometimes not so good, but this is what it is. Okay, so this is all I had to say about this STAs, and I know I'm, very low on time, so I'm not sure if I can take a little bit more time to go through cubic CFTs. It's going to be quick.
Yeah, it's fine. Okay,
great. So now let's switch gears to go to the cubic CFTs. These are conformal field theories that have just cubic symmetry, which is this other type of semi-direct product. If you like your crystallography, this is usually denoted by OH, but it's this semi-direct product. It's also isomorphic to S4 times Z2 in this case. And you can view this as, of course, rotations and reflections on the cube. The order parameter here is a regular vector, but again, two couplings are allowed in the theory. Lambda is the coupling that preserves O3 symmetry, and G is the coupling that breaks O3 down to cubic. Of course, this order parameter could be n-dimensional. You can have a hypercubic theory. I'm mostly going to talk about the cubic theory here. And such deformations appear whenever we have cubic lattices, for example, cubic magnets like iron or nickel. And from recent bootstrap results, we know that we should study them. The situation again is similar to the MN case. There are two fixed points. One fixed point that appears after this cubic deformation is the decoupled Ising theory. So it's up here where lambda is 0 and G is non-zero. And the other fixed point is the cubic, and it either appears for G less than 0 or G larger than 0, depending on what n you put here. If it's a hypercubic or cubic or n equal 2. So in that case, for low n, it starts down here, and as you increase n, it crosses over. It doesn't collide. It just sort of like crosses over the Heisenberg point and goes up here. It's stable for n larger than the n critical, and unstable for n lower than the n critical. We know now from previous epsilon expansion results, as well as the recent bootstrap work, that this n critical is below 3, which means that the n equal 3 case, which is the physical case, is this one for the cubic theory given by the epsilon expansion. But with the Heisenberg and the cubic fixed point very close to each other. So originally, a few years ago, I started to do the bootstrap for this cubic CFT. So the group theory here is quite simple. The traceless symmetric basically of ON splits under the cubic group. It's not is reducible under the cubic group, so it splits into two irreducible representations. I take one of them and I perform this bound, and I find this kink, this sort of like very gradual kink, if you want. And here I showed for you where known theories that should be allowed are. The decoupled is here. The cubic theory of epsilon expansion at order epsilon squared with epsilon sent to 1 is down here. And down here somewhere is also the O3 theory. I didn't put it in. O3 theory here, the dimension of X in the O3 theory is the same as the dimension of the traceless symmetric, okay? Of the 2-index traceless, scalar traceless symmetric. So you notice that the decoupled is not what saturated this bound here. And of course, it's a question if this distance is numerically significant or not. When I pushed the numerics, this didn't move towards the decoupled it seemed to stay stable. So the speculation was then that there is a theory that saturates this bound that is distinct from the theory of the decoupled theory, and distinct from the theory of the epsilon expansion. And with some further work with Stefanos Kouzvos, we managed to isolate an island for this theory, which we call the Platonic CFT. And in this island, we managed to, when we determined the critical exponents, they had these values over here. And just to remind you, the critical exponents for the cubic theory are very similar, of the epsilon expansion, are very similar to the critical exponents of the O3 theory. And they are given by these numbers according to the most precise estimates. And so this theory, this Platonic CFT, appears to be distinct from that of the epsilon expansion. And I should mention that there were these papers of people that did these fixed dimension expansions, but for the cubic theory by Delamotte and collaborators. And they again found hints, just like Pelisetto and Vicari, of non-perturbative, in that sense, fixed points with cubic symmetry that exist for n equal 3 and for n up to 7 or so in their case, distinct from the epsilon expansion theory. So perhaps this is the theory that the bootstrap is sensitive to as well. And I should mention also for this theory and the theory of theories of Pelisetto, Vicari, and collaborators that these are of the focus type. Focus type means that the dimension of the next to leading scalar singlet is actually complex. So this further makes the situation unsatisfactory because the bootstrap, as far as I can tell, does not see such a complex dimension. You know, this is the second leading scalar singlet, right? It should have such non-unitarity perhaps would be expected to have a strong effect on the bounds. If the bootstrap is sensitive to these CFTs, perhaps, and they are of the focus type, perhaps there is something to understand here. Okay, so, and back then I was reading various papers to see what such critical exponents may correspond to, and I ran into a paper by Amnon Aharoni, which said that, well, maybe back then, perhaps his understanding has evolved, I think it has evolved, but back then in that paper, he points out the possibility that strontium titanate has a phase transition which may be described by a cubic theory. Now, the strontium titanate has, perhaps you've seen this picture. Unfortunately, I haven't had time to see Amnon Aharoni's lectures yet, but it has this type of a unit cell where, you know, strontium is here, this red stuff, it's a cubic unit cell. And you have titanium here in the middle of the cube. And then you have this oxygen octahedra in the phase centers. They form this octahedra. And this octahedra rotate below some critical temperature. At room temperature, you have this nice cubic structure. And then at some critical temperature, which is about 105 Kelvin, the octahedra sort of like coherently rotate. This is exaggerated here. And if you think about layers, two octahedra on top of each other, they rotate in opposite directions. So the unit cell transforms from the cubic group to the tetragonal group. So this is this cubic to tetragonal phase transition that is encountered in strontium titanate. And this was measured, I think this was mentioned already in papers by Muller and Berlinger, to have these critical exponents. Back then, remember, this was expected to have the critical exponents of the cubic theory of the epsilon expansion, and there was clear disagreement. And here I'm just mentioning that the current understanding, I think, is that the 3D Ising, due to strain in the material, in the crystals used in these experiments, they're supposed to be crossover to Ising, as has been suggested by Aharoni and others. But here I'm just listing the critical exponents to say that there is still room for agreement with the Platonic CFT, and it would be interesting to us to study what happens if strain is removed. What happens if I have a theory without strain? And it has been suggested in the literature that strain-free crystals also display the same critical exponents. So, as I said, the situation is murky and I think further experiments are required to settle this with perhaps unstrained crystals without inherent strains. Okay, and let me just finally bring to your attention some other paramagnetic-ferromagnetic transitions in these types of compounds that I recently found in the literature. Authors give these numbers. The authors of the experimentalists give these numbers for these transitions that they measured. They're perhaps too accurate, but I'm not an expert to judge the error bars that they give. And here, these authors, the experimentalists, conclude that this number should be Ising. But here, clearly, the Platonic theory does a much better job explaining these critical exponents. Now, these crystals, according to the experimentalists, are supposed to be described by the PNMA space group, which belongs to the orthorhombic crystallographic group, which is not the cubic one. Sorry?
No.
It's probably a mistake.
Oh, sorry. So this is an issue potentially. Perhaps the Platonic CFT, which is derived with cubic theory in mind, perhaps doesn't apply, but that's not clear to me. I would like to learn more about it. And I would like from experts perhaps that are in the audience, why or why not this cubic theory may apply or not to these systems. Okay, so that's all I have to say. So I think it's becoming clear that the numerical bootstrap is a widely applicable method and a very good method for the study of these systems. There are many experimental results also reviewed by other people here with unsatisfactory results from theory and experiment. It's a great time for the bootstrap to resolve some of these. New non-perturbative classes have been suggested, and the big question, of course, is if the Landau-Ginzburg paradigm is incomplete, and we're missing theories that are not connected to this 4 minus epsilon theories in 3D that are not connected to the to 4 dimensions continuously, as in the 4 minus epsilon expansion. I hope that the new tools presented in this workshop and the discussions with experts will allow us to make further progress on these very interesting questions.
All right, thanks a lot, Andres, for this very nice talk. So yeah, we have time for questions.
I wanted to go back to this focus fixed points that you mentioned.
Yeah.
So I'm not sure if there are like all of the fixed points found by Vicari, Calabrese, and others who are focus type, or maybe just some of them. But I just wanted to say that as far as I'm concerned, like all the fixed points which are focus type, you can just as well just throw them in the garbage bin and forget about them. For the same reason that you said there is a unitarity constraint in these systems, that the systems that they are studying are reflection positive, and so they cannot, in physical dimension, in dimension 3, show complex values of critical exponents.
Maybe the method produces these imaginary parts which are non-physical, but you don't want to throw the baby out with the bathwater, right? I mean, maybe the presence of the fixed point is signaled by the method, but maybe it doesn't give the right answers for some dimensions.
Okay, let's say they have to redo the calculation, and if they redo it in a way which gives fixed point satisfying constraints which we know on general grounds, like the fact that the critical exponents should be real and so on, then we can consider it seriously. Otherwise, because what is happening is that they take their beta functions and they resum the beta functions. So they take beta functions computed to some finite order, and then they resum the beta functions. Well, we know, thanks to the work of Hugh, Osborne, and others, that the beta functions in high orders, they satisfy some very non-trivial constraints, following from like gradient structure in the beta function and so on. So if you just resum beta function blindly without paying attention to its constraints, you can basically get whatever garbage. I mean, you'll get whatever you want. So
yeah, so I think for us, for the bootstrap, it's an interesting question to ask. Okay, maybe the method gives garbage, or to some extent gives garbage, but is the bootstrap sensitive to whatever that method gives or not?
Well, I mean, I would just say you have your fixed points, and if you have them, great, but you should not compare your fixed points to some clear garbage. I mean, we should just be careful. I mean,
I want to, okay, fine. I mean, I want to represent, as I said, I'm not making any strong statements. I'm just, I wanted to give an accurate representation of the state of the art in the literature. This is, I want to pass judgment on others' work.
That's not state of the art. When I confronted Calabresi with this, he said, okay, well, at the time I was just a PhD student. I didn't know anything about unitarity. This was my first paper. So okay, I don't care.
But I should say, I came to this slide to say that there was a recent Monte Carlo simulation by these people, and they also saw some fixed point. And for some reason, although the critical exponents don't agree very well, okay, it doesn't matter. They also say that they see signs of focused behavior in that the approach to the critical point is some spiral approach. And they interpret that as an imaginary part for the relevant, for the operator.
Do they comment on the fact that this contradicts reflection positivity? Is the model that they simulate?
They don't make any comments like that. So
okay, this just means they're incompetent. Well,
okay, that's okay. You can say that. I didn't say it. You said it, and
yeah,
you have the right to
I
say
can
it.
afford saying that.
I'm confused. In the old days, at least, people showed that the beta functions are gradients of a potential in the parameter space, and therefore the flow is a potential flow, and then you cannot have you cannot have complex exponents, and two, that typically in such phi to the fourth theories, you have only one stable fixed point. I think there were proofs of that by Wallace and Zia in the early days. I think Louis Michel also worked on that problem. I wonder how all that
within the standard. These are results within the standard epsilon expansion. So, yes. And Hugh, of course, has extended a lot of these results to higher order, and but anyway, and of course, the proof for the stability of the fixed point being for the stable fixed point, if it exists, being unique, is a general proof by Michel. I think the point here is that these are all proofs within the standard paradigm of the epsilon expansion. But these calculations of these people, and certainly the bootstrap, goes well beyond that. So we are in the unknown. These proofs don't necessarily apply to these methods.
No, but
I don't think it's special.
No, but Amnon, I think the point is that
the people who do the flow of the RG in 3 dimensions, they flow in the space of the G, the coupling constants, And they do it in 3 dimensions, and I think that that flow also should be a potential flow.
Yes,
Yeah.
but here they do certain resummations of those beta functions before they look for fixed points.
So what they should do instead, they should construct a potential function, resum the potential function, not the beta function itself, and then they will not find any complex fixed points. But they resum the beta functions, and when they do this resummation, they violate this this property that that Amnon is mentioning, and that's clearly the source of the error. But Amnon, just a comment as a comment to what you said. So you mentioned 2 facts. One fact is that the critical exponent should be real because of this gradient property, and the second fact that the fixed point should be unique. Now,
Yes,
from
I'm
our
not sure how general that theorem is, but
Yeah,
in the old days
think,
at least, that was the rule.
So we think that the theorem about real critical exponents, it should be very general within a certain class of theories which are reflection positive, should be non-perturbatively valid. That's very general. While the theorem about the uniqueness of the fixed point, well, that may or may not be true non-perturbatively. We don't know.
I'm
Probably
asking
not.
the question. I don't know.
So just a point on that, if you believe that these 2 kinks here are both true kinks corresponding to true CFTs, which is a belief you don't have to share, then since both of these are stable, that would be a violation of the epsilon expansion result that two CFTs can have, 2 CFTs cannot be simultaneously stable within the same coming from the same set of deformations, here respecting this symmetry. So this would say that perhaps this fixed point can be found with the epsilon expansion, but this cannot.
Hi, Andy. So when you were mentioning that there were problems with the epsilon expansion to find the cubic fixed point from 4 dimensions, I was just wondering, do you know if there are conformal perturbation theory results about reaching the cubic fixed point from the 3-dimensional O3 model? Because
there are no problems finding, maybe I misspoke, but there are no problems finding the epsilon expansion of the cubic theory of the epsilon expansion using the epsilon expansion is a standard calculation. There are no problems finding it.
Yes, but do we believe the results particularly from setting epsilon equal to 1? Or is
because they show, so this is, of course, for other operators, not for this X operator, but for other operators, these results have been computed up to order epsilon to the 6th, I think, again, by Compagnietes and collaborators recently. And with resummations, with blah, 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 they find a very good agreement with the O3 critical exponents, which is what we expect, given the fact that in theory space, if you want in this space, the cubic and the Heisenberg fixed point for n equal 3 specifically are very close. So their data should be, wherever there is overlap of overlapping data, like say the leading singlet, should be very similar. So this is what the epsilon expansion shows. This is what the bootstrap recently has shown. Oh, sorry, the bootstrap has not found the cubic theory of the epsilon expansion, but it has shown that the cubic theory of the epsilon expansion and the Heisenberg fixed point are indeed close in theory space. And I think it was discussed that there will be efforts to determine the appropriate coupling that will allow us to do conformal perturbation theory from the Heisenberg to the cubic fixed point, which would give a new understanding, a new way to understand the observables scaling dimensions and perhaps opaque coefficients of these, of the cubic CFT from conformal perturbation theory from the Heisenberg fixed point.
Exactly. That's what I was asking about, because that would be.
Yeah, it hasn't been done, but in order to do that, as far as I understand, and this is something Ning mentioned, I think, that's during his talk, you need the coupling of the Wilson coefficient of the 4-index traceless symmetric in the OPE of 4-index traceless symmetrics in order to study this flow, because that's what triggers the flow. And you need, and correct me if I'm wrong, if someone knows better, but I think that's what the result is. So to get access to that, you need to do an even larger bootstrap problem that has been done already. And this Ning, I think, and others will attempt to do. Ningsu.
I have a question in another direction. In the NM component problem, you have the decoupled fixed point in which you have n decoupled M component models.
Of course.
And the stability exponent for the coupling between these decoupled models are known exactly. My question is, does the bootstrap calculation of those stability exponents agree with the exact statement? They're related to the energy, to the dimension of the energy operator in the M component model.
Yeah, so what we know from the bootstrap is that for n equal 2, the dimension of the leading singlet of O2 is above 1.5. That means that when you take decoupled O2s, two decoupled O2s, you will have the next to leading scalar will be twice that dimension, so it will be above marginality. So that the decoupled O2 model is supposed to be the stable one, and not this model I showed you here in the first kink. Here in the first kink, this MN 2,2 first kink is supposed to be unstable to the fixed point that is decoupled O2 models. It has the same symmetry, but it's decoupled. This
But
is
that fixed point is unstable, and I'm asking about the exponent taking you away from that fixed point, the instability exponent.
the crossover exponents you meant.
The operator that couples the two decoupled vectors.
This the next to leading
energy coupling.
Yeah, I haven't. Are you asking if I know the dimension of that operator? Is that what you're asking?
No, I mean, I understand. I think I understand the Amnon's question.
Exponent directly from the bootstrap, and if you calculate it given your knowledge of the exact expected value from two M component models, do the two agree with each other?
Andy, can I translate the question for you? Because I think I understood what Amnon wants.
Okay.
So Amnon is asking the following question. So we know, let's take the model, decoupled model, which is not the model in this plot. He asks if you can set up a bootstrap calculation, which somehow, even though the model is decoupled, nevertheless extracts all the dimensions for the decoupled model and demonstrates that the dimensions are indeed sums of the dimensions of the decoupled CFTs.
Of the decoupled copies.
Yeah, of the decoupled copies, yeah.
Well, in principle,
once you switch on the coupling, then it's no longer decoupled, right?
Yeah. No, in principle, in principle, of course, you should be able to do this, but we wouldn't do it that way. We would just go to the O2 model and use the fact that it's decoupled to deduce those values. But in principle, yes, you could go.
As a test for the bootstrap method.
Yeah, in principle, so that model is in the allowed region here. So if you had some way to go to it and do all the bootstrap stuff, and yeah, it should just be a solution to the bootstrap equations just as well as this one is a solution to the bootstrap equations. There is no reason why it wouldn't be.
I mean, Amnon, as a comment, I can just say that I mean, we are not masochist, right? I mean, if there is some obviously true non-perturbative result that the dimensions in decoupled theories add up, we use it. In the bootstrap philosophy, you have to use all the rigorous. I mean, you can try to set up a calculation to do this, but I mean, there are many more interesting calculations to set up, which give results in agreement with other things. So, I mean,
okay,
we are not masochists.
Sorry, the Platonic CFT, remind me, have you studied in the varying space-time dimension or not?
Yeah, we studied this in varying space-time dimension, and I studied this in my paper some time ago, not in terms of islands, but just to see how the kinks move. And it persists. I studied up to dimension 3.8 or 3.9, I don't remember now. And I couldn't reach very solid conclusions because it starts to, the cubic CFT of the epsilon expansion and this kink, they start to get closer together. And it seems that it persists. So this might have an explanation in terms of the epsilon expansion, perhaps including different degrees of freedom as well. But I haven't made any progress in understanding this more.
Yeah, I think as a comment, that right now we have to do the bootstrap. There is this like kind of trichotomy. We have to do the bootstrap, and then we have to compare it to 1 over n, and then we have to compare it to epsilon expansion resummed by some other people, and so on. But I think soon we will be able to completely become independent from the input from these people, because we no longer have to use the resummed epsilon expansion. We can just do the epsilon expansion using the bootstrap, and we can extract very good results for critical exponents as a function of epsilon. And we will be able to connect, I mean, in the very near future, we will be able to connect any theory from 4 minus epsilon to 3 and see how things go, how they appear, disappear. We will be able to completely like circumvent this current dependence on this dark art of people doing resumations. Soon it's going to be not necessary, I think.
And that will be great, yes.
Yeah. So we just know that there are theories, they move in the theory space as a function of n, as a function of epsilon, and we will be able to study these curves exactly, I mean, like non-perturbatively. And then, yeah.
I shall have some comments on that in my next lecture.
More questions? Okay, if not, let's thank Andres again.
I stopped the recording.
You can stop the recording.